I'm actually going to make a video. This is for Unit 3, Lesson 1, Energy Flows and Causes of Change. So this Lesson 1, all the explorations are talking about how energy flows from one thing or form to another and how it causes changes. So here's a picture of the Three Gorges Dam. We do skip over these questions, but I will mention them just uh, in passing. So this is, how would you define a flashlight as a system? What's its inputs and outputs? What are parts of the system? So and the crank has the energy of motion when it's turned on. What other types of energy might the flashlight have when the bulb is on? So first, the flashlight is a system because it has multiple components, right? There's a bulb, there's the crank, there's things inside. It has inputs and outputs. So the input would be you winding it. When you're winding it, that's what we would call mechanical energy. You're putting energy into it by physically winding it, and then it's outputting. This is kind of like number two. What energy is it producing? It's producing light energy, which is um, electromagnetic radiation, and it is producing heat because the bulb would get hot, and so those things are outputs as well. So that is what makes it a system, and uh, the inputs and outputs, and what types of energy it's making. So getting into exploration one, I'm going to go through all of the explorations all in one video, and so I'll go further. If you're looking at exploration one, I might be going past that, but you can just fast forward and rewind and whatever. So exploration one is on identifying different forms of energy, and three says discuss what types of energy you can identify in the photo of the tornado. So now you might not have all these because we're just getting into energy and forms of energy, but I would say there's heat energy because I know that tornadoes form because the different temperatures in a storm. You can see that there is energy. There's like wind energy, right? The trees are all kind of diagonal. So why don't I say that? We have wind, we have heat. These things are part of weather. I'll leave it at that. Those are some things I can identify. Maybe similar to what you would say. Okay. So the first type of matter that we are talking, or the first type of energy that we're talking about. The first type of energy we're talking about is kinetic energy, right here. Kinetic energy. So kinetic energy is energy that moving things have. That's why it says the energy of matter in motion. So this says the energy that an object has due to its motion is called kinetic energy. All moving objects have kinetic energy. So, and then we get to number 4, and it starts talking about kinetic energy. So number 4 says, what evidence could you use to compare the energy of the two balls? Which ball do you think has more energy? Write your answer in the table. So one of the things that it mentions up here is that in order to have kinetic energy, you have to have mass. Where does it say that? Oh, it doesn't say that, but it says matter, and things have mass. Oh, here we go. A bowling ball has much greater mass than a tiny ball. What would happen? So one of the keys with kinetic energy is that here we have two examples, and we have the important thing here is that both balls are rolling at 2 meters a second. So both of these are rolling at the exact same speed, but obviously the bowling ball weighs way more, has much more mass than the pinball. So the bowling ball has more kinetic energy because there's essentially more that's moving at the same speed. And so since they're both moving the same, the thing that has more mass also has more energy. So let me make this text a little smaller as I go through these. More mass, so more energy. Less mass, less energy. Now, that isn't always the case, right? Because that's just the case here because the balls are moving at the exact same speed. So you also have to take into account the speed of objects. Because remember that kinetic energy isn't just everything has kinetic energy. It's things that are moving, right? So since they're moving, you also have to take into account their speed. So in this example, we have two different bowling balls, and they have the exact same mass, but this bowling ball is supposed to be moving faster than this bowling ball. So this one is faster, so it has more energy. Slower, so it has less energy. And we can say that about these two because everything about these is the same except the speeds, right? Same bowling ball, same weight. The only difference is that this bowling ball is moving faster than this one, so it has more energy. And you could see that if you've ever gone bowling in real life, if you have a bowling ball, it's harder for you to make the bowling ball go faster than slower. You have to push it harder. You have to put more of your own energy into it in order for it to go faster. So that kind of makes sense. All right. Now, moving on from kinetic energy is usually talked about in tandem or along with potential energy. Potential energy. So, potential energy, the energy stored in an object due to its position or condition is called potential energy. For example, increasing the height of the ball will increase its potential energy. So, what does that mean? So, the idea is that you can see this ball right here. Now, if this was balanced perfectly, it's not moving, right? It has no kinetic energy. It's still. But let's say I nudged it one way or the other, right? It will roll this way if I bump it that way. Or if I bump it from this side, it's going to roll that way. That is what we call the potential energy. So if you had another hill, let's say you had a hill over here, and it was only like this high, right? And then you had another ball on top of that one, right? This one would have less potential energy. Well, why does it have less potential energy? Well, it's because the hill, right? It wouldn't get as much if it had to go down, right? When it's at the bottom, after it's sped up all the way, it would be going slower, right? Than this one. If this one I nudged down a taller hill, it would get going faster. So it has more potential energy. Think of like if you had, like Hot Wheel cars on a racetrack type of situation. If you make a tiny hill, or even on like if you're riding a bike, if you ride a bike down a tiny hill, you don't get going really fast. If you're on a high hill, you're going to go faster. That's potential energy. So this says, think about how the ball's energy changes at different points on the hill. At the top of the hill, the ball's potential energy is at its maximum. So it's sitting there, it's not moving anywhere. So it's got maximum potential energy because it has the most potential for going somewhere. As the ball rolls downhill, its kinetic energy is increasing and its potential energy is decreasing. So because as it goes down the hill, right, imagine you're rolling it down the hill, it's going to start speeding up, right? And it's moving more. That's more kinetic energy, but it's also its potential energy is decreasing. So it's kind of a balancing act. As one goes up, the other goes down. And at the bottom of the hill, the ball's potential energy is at its minimum, right? Pretend you actually rolled this ball down the hill. It didn't go whoop and stop magically. Right here, it's at its fastest, especially if it might be easier to imagine that this hill doesn't exist. If the next hill didn't exist, right? The ball would be going at its fastest right here when it kind of flattens out, and then it would start slowing down. So right here has the maximum kinetic energy because it's moving at its fastest. So, and its kinetic energy as its maximum. But its potential energy is at the minimum. Because remember, potential energy is the potential that it will get kinetic energy. And if you're a ball and you've rolled to the bottom of the hill and it's flat now, there's nothing that's going to make you go faster necessarily. So you're just going to start slowing down. So you don't have any potential energy anymore. And then this kind of talks about how as the ball rolls back up the hill, in theory, now its kinetic energy would be decreasing because the ball is going uphill, so it's going to be slowing down, so its kinetic energy is decreasing. But now that it's going back up a hill, right, it will start gaining back potential energy because if the ball stops, or if it gets to the top of the hill, it has the potential to, go back and roll down. So down here it says, just as the ball on a hill will naturally roll downward because of gravity, the water at the top of a waterfall will flow downward. Before they move downward, they have potential energy because of their positions. The potential energy of an object due to its height or position relative to Earth's surface is called gravitational potential energy. So a lot of times it's the term gravitational potential energy when you're on Earth, because it's the whole concept of if you're up high, what you're getting the potential energy is coming from gravity because gravity will pull you down to the lowest point. So raindrops move from clouds where they have more potential energy to Earth's surface where they have less gravitational potential energy. Right when they're in the sky, there's a lot of potential for them to go somewhere, and the potential is for them to go down. But when they're on the Earth's surface, there's very little or no potential for them to continue going down. Even if you're like, say, right here, a water drop from here, you have potential to go down to the waterfall, but you still have less potential energy than when you were way up in the cloud. Where does the water in the photo have the least gravitational potential energy? At the very bottom. So the lower down you go, the less potential energy you would have. Okay, and now we have forms of energy. Now we're going to talk about this more in class. I'm going to go through this pretty quickly, but essentially this section is on how there are different forms of energy. Some of them are kinetic energy is one, potential energy is another. So it says, you can see potential energy is due to its position or condition. Kinetic energy is from motion, right? And then we also have thermal energy, sound energy, electromagnetic energy, electrical energy, chemical energy, nuclear energy, gravitational potential energy, and elastic potential energy. These are all different forms of energy, and we're going to kind of go into these more. But for now, we're going to start with mechanical energy. So mechanical energy is usually one of the easiest to understand, and it is an object's ability to move or do work on other objects. So a lot of times when we as human beings are doing things, using a hammer, riding a bike, walking, those are described as being mechanical energy types of things. Other forms of energy. So in here it talks briefly about other forms of energy. So we have the sun is driving forms of energy. The sun is electromagnetic or radiation type of energy. Thermal energy is the movement of energy particles. Is the kinetic? See, it says thermal energy is the kinetic energy of particles. So that's heat and cold. Is what we describe as being thermal energy. Sound energy is caused by vibrations in the particles that make up matter. So sound is similar to essentially, wind. Wind is the movement of particles, and sound is the vibration and the waves within the air. That's like if you go to space, there actually isn't sound because there's no air for the sound waves to travel through. And you kind of skip this one. Then we have applications of mechanical energy. So this says objects tend to come at a rest in a position of lowest potential energy. Think of a machine or system that works against this tendency. Describe how kinetic energy is needed to increase the system's potential energy. So what this talks about is, and I'm going to use this example. So this here talks about an obelisk. So it says 25-meter stone pillar called an obelisk stands in the center of St. Peter's Square in Rome. An obelisk is like so it talks about how workers and horses used winches to pick them up. So an obelisk, if you haven't seen it, they're like those big, or it's like the Washington Monument is an obelisk in Washington, D.C., and they are those tall, you only have a triangle, and then they are usually, like those, oh, that's a very bad line, but, they're those straight type of tall buildings. It's called an obelisk. So this question is asking, what machine works against this tendency? And that tendency is the tendency for objects to come to rest at lowest potential energy. Meaning when they don't have any potential energy, they kind of stop moving. So one thing I can think of is a clock. A clock uses a pendulum in order to keep the gears rotating. I want to move this over. So an old school type of clock has the pendulum that's rocking back and forth constantly. And that's an example of, it's trading in kinetic energy for potential energy. So it goes down and it gets kinetic energy, and at the bottom it has the most kinetic energy and the least potential energy, and then it kind of goes up, and then it's trading back and forth. And one of the things that helps keep going is because as it goes back and forth, it's losing some energy, but clocks have weights inside to help the movement of the gears. So that would be the something that helps it kinetically, because the kinetic, the weights have potential energy to pull down, but also kinetic energy is needed to bring the pendulum back up. And how might our machine or system be improved? There's lots of answers for this, so out of time I'll just explain instead of type. But you could, if you had a big clock, the best way to make it go for a long time is make sure that the pendulum is perfectly balanced so it can swing back and forth with the least resistance, and that the gears and everything also have the least resistance. So you might want to use less gears, or lubricate them well, or just have it built really accurately. Okay, exploration 2 now. Observing energy transfer. So this exploration is about how energy transfers from one thing to the next. So 12 says, what happens to the kinetic energy of the bowling ball when the ball hits the pins? So when the ball hits the pins, these ones I'll probably go through a little bit faster than the first exploration. So when the ball hits the pins, the motion kinetic energy will be transferred to the pins from the bowling ball. So, hold on. Oops. Predict what will happen if the ball rolls straight into an object with a greater mass than a bowling pin. So, in this situation, we have a ball is rolling into something that has more mass than these bowling pins. So, if that happened, so in this case, if you've ever held a bowling pin is pretty light in comparison to the bowling ball. The bowling ball has a lot more mass. So let's say that there was, the pins were much heavier, or there was like a big block of concrete here. Well, what would happen? So the kinetic energy would still transfer from the bowling ball, but it could happen faster or more, so the ball would slow down faster. So the general idea is, in order for this ball to stop moving, it would have to transfer all of its kinetic energy into all of the pins. Now, since the pins are so much less mass than the ball, that's why the bowling balls fly through the pins and knock the pins all over the place, right? Because it's transferring some of the bowling ball's energy, but not all of the bowling ball's energy. If you had a giant concrete block down here, you might roll the bowling ball down, and the bowling ball might slam into the concrete block. And you might see that the concrete block moves a little bit, but the bowling ball would probably stop pretty quick or instantaneously because it has because when it hits the giant block of concrete, the block of concrete has so much mass that it can absorb all of the kinetic energy of the ball right away, and it moves a tiny bit because it has so much more mass, but essentially it takes all the energy away. We are going to skip this for now, and we're going to go to energy transfer in collisions. So this is kind of talking about what I just said. Like, you roll the ball and it hits the pins and it's transferring this energy. So when you see that the ball slows down, it's because some of its kinetic energy has been transferred to the pin, and that's why the pin moves. You can see that with these pendulums. So this says 2 pendulums are set to collide. Identify where the swinging pendulum has the greatest potential energy and where it has the greatest kinetic energy. So this is this would be the greatest potential, and this is the greatest kinetic. One thing is, when you're looking at both of these balls right here, neither of them is moving. There's no kinetic energy happening. Here you see it's blurry because it's moving. The ball is still moving. It's crashing into this other one, so it has the most kinetic energy. So this is called a Newton's cradle, and this is a perfect example of how this works. If you've ever seen one of these, you can hold the ball here and you drop it, right? And what it does is it hits the end, and because there's so many of these are normally like steel or aluminum balls here, because there's so many of them, this ball, when it hits the end, it usually immediately stops. Like here, it'll hit the end and it'll stop. But what happens is it transfers the kinetic energy to the second ball and the third ball and the fourth ball, and then that energy gets transferred to the fifth ball, which then shoots up the other side, and then it comes back and it hits. And so what you end up with the end balls kind of like knocking back and forth because it's transferring the energy through the center ones. So we're skipping this one because it's just kind of drawing out that same thing. You can see transfer of energy in this picture where the water has kinetic energy that's moving and it transfers it to the wheel, right? And so then the wheel is moving through mechanical energy, and then this wheel is transferring its kinetic energy or movement energy to this wheel, which is spinning this like what looks like a stone. Like this was pretty popular back in the day to have water wheels, and they would spin stones to like grind grains and things like that. This says, describe the transfer of kinetic energy that occurs between a person and the crank of the hand flashlight. Record your evidence. So when you are, I kind of said this at the beginning, but if you are hand cranking a flashlight, that is mechanical energy, right? You're physically moving this hand crank, and then it's getting turned into like electrical energy into the flashlight, because the hand cranking is a kinetic energy of your hand moving, and then it's moving gears and things inside that will generate the electricity. And 17 says, one idea for avoiding a catastrophic collision like space debris with Earth is to use a missile-like projectile to knock the object off course or deflect it. So this was talking about a giant asteroid that came in and created essentially what was like a giant nuclear blast almost. And this is describing, so let's say that you are Earth. Here we are on Earth. Yay. Earth. Here's an asteroid. The asteroid is heading towards Earth. Uh-oh. So what this is describing, one idea is to use a projectile to knock this off course. How can scientists be sure to create an impact with enough kinetic energy to change a meteoroid's course? What factors should they consider? Well, like we've talked about before, things that they would have to consider is how far away it is, right? So let's say if it was a really small asteroid and you could just take a little missile and you launch your missile, it goes into space and you go off, and then you go crashing into it, right? What's that going to do? It's going to bump. It's going to transfer some kinetic energy to the asteroid, and instead of the asteroid continuing to go straight, it's just going to go a little bit more sideways. It's going to bump it so it'll go this direction, and then it would miss Earth, right? So that's the idea. Well, what things do they have to consider when they're doing that? Well, you'd have to consider things like if it's a really big asteroid, you'd have to knock it off course farther away, because if you only shoot a tiny missile at something, it's only going to move it a little bit, right? If it's small, it could be maybe closer. But you have to consider things like that, because it's just like if you were, for example, if someone was, like if you're throwing a baseball. Let's say you're throwing a baseball. If you throw a baseball and someone like tips it with, like, let's say someone's standing next to you and you're holding a baseball. This is a bad example, but it's the only thing I can think of right now. So let's say that someone is holding a baseball right now, or no, I'll think of hockey. Let's say hockey. They do this all the time in hockey. So let's say someone in hockey, you have a dude who's playing, and he's got his little hockey stick, and he shoots the puck that way, right? If you have someone way over here, way back here, right, and they want to deflect the hockey puck, they can deflect it, but let's say they barely touch it. If they barely touch the hockey puck, right, the hockey puck is going to be deflected a teensy little bit, right? But from there, if you have someone over here, way closer, and they deflect it, right, it's going to be deflected here. So it's going to start going this direction here. So what am I trying to say? if you wait longer, right, then you can see how the puck would go off in this direction. If you do it sooner, it's going to go farther. It's going to be in a different direction. So if you're Earth and you're here, and this is, missiles, not hockey pucks and a meteor, you don't want to wait till the last possible minute to knock it away and have it maybe miss Earth, maybe get sucked in through gravity and hit. You want to do it when it's real far away, so it gets deflected and it's going way off in a different direction earlier. Those are certain things you'd have to consider. Okay, finally, exploration 3 and modeling energy transformations. So why do you think the Newton's cradle stops swinging? What does this imply about the energy in the systems of pendulums? So it stops swinging because there is resistance in the wire, in the air, other things. So these are things called, why isn't this what we would call a perpetual motion machine, where it just goes on forever and ever and ever? And that's because in reality, there's air that these balls are going through, right? So just like when you throw a baseball and it slows down because there's air that it has to go through, these balls on the end are going to constantly be having to push themselves ever so slightly through the air. And also, you can see how these don't perfectly transfer the energy. These probably aren't perfect spheres. They're not floating in free space. They're held down by these wires. So all this tiny little bit of resistance is also where some kinetic energy will be lost. Kinetic energy will be lost to the air as the ball's pushing through the air to move the air molecules out of the way. It'll be lost to the wires through vibrations. And so as energy slowly kind of leaks out, it will eventually stop. Think about other collisions, about different forms of energy, what other forms of energy might result from collisions from Newton's cradle. Oh, here's some other examples. What's happening with this that you see? Well, you might, I think the easiest thing would be sound. Right? You're going to hear these balls click, 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 clicking back and forth. So the sound is energy that's being formed from kinetic energy to the, I'll say, to the motion of the atoms in the air. Right, so what happens is as the metal ball hits the next one, it is quickly pushing lots of atoms out of the way, and it's creating essentially a sound wave, which is a pulse in the air that our ears pick up. So that's a type of energy. That is what we call an energy transformation. So there are different types of energy, and whenever energy goes from one thing to the next, we call it an energy, it's right here, an energy transformation. So here's different types of energy transformations. So fireworks is an energy transformation, right? It takes chemical energy. The chemical energy is because the fireworks are made from basically, a bunch of chemicals, and you shoot them up into the sky, then it explodes. And so it's turning into electromagnetic energy, which is the light that you see, the sound, the heat. We've got electromagnetic energy and sound energy coming from computers and TVs. Batteries are chemical energy that gets converted into electric energy. And like wind-up things are, you're using mechanical energy, you're physically winding something, and it's getting converted into electric energy that we can use. What energy transformations occur in the hand creating flashlight? I mean, we've talked about this a little bit before, but it's the same as this. you're transferring your mechanical energy, and that's being transferred into electric energy, or you could even say thermal energy from the heat from the light bulb. This is okay. And then here we have this one. This is the last thing we're going to wrap up. This is math about light bulbs, and this is actually kind of. I recently replaced all of the light bulbs in my house with LEDs because they use way less energy and they last a lot longer. So this says the flow of energy through a system can be expressed in watts. So you can see here is watts. This is how much energy is being flowing through the bulbs. And then 1 watt is equal to the flow of 1 joule of energy for 1 second. This table shows data for 3 bulbs that produce the same amount of light. Electrical energy is often measured in kilowatt hours, the amount of energy used in 1 hour at the rate of 1,000 watts. So this is how much watts or how much energy is flowing through these light bulbs, and this is how much energy is used over an hour. So this says, suppose the price of electricity is 12.75 cents per kilowatt hour. Okay, per kilowatt hour. These are already in kilowatt hours. What's the difference in cost in dollars between the use of an incandescent bulb for 2,000 hours and an LED bulb for the same amount of time? So in 2,000 hours, right, for 2,000 hours, this is for 2,000 hours. So to figure out the cost, this is 12.75 cents per kilowatt hour. And so we need to figure out these are the kilowatt hours, and you got to figure out how much they cost. So the incandescent is like the old school Edison-y bulb. So the incandescent bulb would be 120 times 1275. The LED bulb would be 20 times 1275. So let's see what those are. So 125, 12, 1,530 dollars. That's a lot of money. And 255 dollars. So the LED. So for 2,000 hours of use, which I mean, if you think about it, and how much you have lights on, that's not that much actually. The incandescent bulbs would cost you $1,500. The LED would only cost you $255. How much more energy in joules does an incandescent bulb use than a CFL in 1 minute? So in 1 minute, remember this says that the watt is equal to the flow of 1 joule of energy for 1 second. This one's energy in joules for 1 minute. So in 1 second, the incandescent uses 60, and the CFL uses 14. So it is 46 more per second. So to figure out the minutes, it would be 46 times 60 for 60 seconds. And that equals 2,760. And then finally, 24 is hand-cranked flashlights transform mechanical energy into other forms of energy. Which energy transformations are useful and which are not? Explain why most hand-cranked flashlights are made with LEDs. Using this up here, hopefully you can see that the LED is much more efficient, right? Because this is they said that these have the same brightness. So if all of these bulbs are the same brightness level, the LED is using way less energy. So where's all this energy going if the LEDs are just as bright? Well, incandescent bulbs are super inefficient because most of it is through heat. And this kind of describes this picture of a laptop you can see is an infrared and you can see how all this red is showing that this laptop is losing heat, and that heat energy is coming from its battery. Um, so a lot of the energy that this computer is getting isn't even being used by the computer. It's just leaving the computer as heat. So why would most hand cranked flashlights be made with LEDs? Well, if you have to crank a flashlight in order for it to be on, right? You don't want to be cranking a flashlight and have, you know, 3/4 of your, or look at this, 60 compared to 10. You don't want to have to, let's say that you had to, this one you'd have to wind, let's say, one time for a certain amount of energy. This one you'd have to wind 6 times for the same amount of brightness. So, if it was just these two bulbs, you'd have to be winding 6 times as much if you weren't using an LED, because you'd have to be producing a bunch of energy that just gets lost through heat or through other things like that. If you use an LED, it's much more efficient. So you wouldn't have to wind as much. You wouldn't have to use as much energy. So, yeah, this is why one of the big things that people talk about when they talk about climate change is getting rid of incandescent bulbs, because it's not really that they produce heat, it's just that they are super inefficient with their energy. And you can see, so people always say you should buy LEDs, and LEDs do cost more at the beginning. An LED bulb is more expensive than an incandescent bulb, but they last way longer, and they actually cost way less because they use less energy in the long run. So, yep, that is all for the entire lesson 1.